So I am showing on the screen right now the tutorial file you should have downloaded from the school website or from the wiki site of Topaz. And I highly recommend this because it also has part of the theory that I have shown, and I will continue to show you this during this talk, and some details I cannot go over, of course, for reasons of time. And then there is the explanation of how to use the files using Topaz. So you can just step by step proceed by clicking the right things, and there is the explanation of what is it about. So this is how to use the double void approach, and then you go on and you see how to use the other approaches. So it is very convenient. So please read this, maybe with more time when you go back home. And these are the files, by the way. You should have no, these are not the files. Yeah, these are the files in the tutorial you find. During this 1 hour or so, we will go over one or two of them, okay? But then you can see the others on your own. So let's go back to where this. Oh, actually, I like the sentence. Is a comment. Oh, I have killed completely the talk. Okay. I have a touch screen, but it is a little bit touchy. So, okay, touchy. Okay, so the sentence at the bottom, for those of you who can read it, convolution in one domain, reciprocal inverse length space, reciprocal space, equals pointwise multiplication in the conjugate domain, which is the space of real lengths. So this is the basis of the method. So as I was saying in the morning before lunch, this is the trick, that the convolution of the effects from the size of the crystal, from the dislocation, from falls, from whatever you have in your microstructure, can be turned into a multiplication of Fourier transforms. So now the question is, where do we find the Fourier transforms? Now, let's start with the simple thing, the instrument itself. Here I call this instrument T, the Fourier transform. And I don't need to take care of this with the Topaz. This is one of the beauties of Topaz, because it's built in. It's the fundamental parameter approach. And we have already go over this, and with Robert Dinever, he has shown how you can obtain it for your instrument. So once you do it for your instrument, let's say you don't need to touch this anymore. So let's forget about that. But if you like, this is more or less what I've shown you in the first lecture, how I describe this instrument, for example. But it's just an example. So now let's see the other terms. First of all, the size broadening, where the Fourier transform of the line profile comes from. It might look like a very complex thing, but in the end, it's pure geometry. Geometry can always be solved and worked out. This is by definition, a theorem on that, but geometry is just geometry. So what is the geometrical meaning of this Fourier transform? It's the following. Let's imagine that you have a simple spherical crystal. This is just for starting. So with a given volume and diameter. Now, the Fourier transform is related to this intersection volume between the sphere and the same sphere translated along the scattering vector direction, and then normalized to the volume just for convenience. This is the Fourier transform. So you take any object you want, your show, and you move it outside itself like a ghost, ectoplasm, along the scattering vector direction. The intersection volume is the Fourier transform. Now, you like to see what is the like in formulas. It is an easy geometry problem. You don't need a university degree to do that. This is the volume, intersection volume between two spheres, easy. And it is this one. D is the diameter, L is the distance along the scattering direction. Clearly, it goes from 1 when the ghost and the sphere are one into the other, and then it becomes 0 when the sphere is completely out of itself. And it is just a polynomial. So it turns out, we kind of demonstrated this, I think, that it is always a polynomial as far as you have polyhedra. So if you have polyhedral crystals and spheres, the common volume, that's the way we call it, is always a cubic. So it is just a matter to find the coefficients of this third degree polynomial. Geometry, easy. So let's see the application. This is a simulation of a pattern from a powder of spheres with the same diameter d from this Fourier transform. You just back transform it and you have the powder pattern. Okay, peak by peak. So the thing is pretty easy, but now let's see something more complex. What if it is not a sphere, of course? What do you have to expect? So let's take a shape which is think of a polyhedron, of course. And then you know that it is still a function of some coefficients, but now they will be different depending on HKL, because the thickness of the crystal is different. So if you push the crystal outside of itself in one direction, blue intersection, or in another, red intersection, you clearly have different Fourier transforms. And then the crystal will appear smaller and larger accordingly. The more the Fourier transform is steep, that means the tangent in zero goes down steep, the smaller the crystal. There is an exact relation with the integral breadth, full width of maximum. I don't want to go over those formulas because we don't need them anymore. We don't reason anymore in terms of width, but in terms of Fourier transform. So what you will get is this. You will have two peaks. One is broad and the other is less broad, just because of the different shape of the Fourier transform. This, as I say, is pure geometry. It's just the volume of intersection between your crystal and the crystal itself translated along the scattering direction. You can always calculate this. Now, let's face another problem. Your crystals are not all equal, and you have a distribution. I can assume, for simplicity, an analytical distribution, just because it's just a function of two parameters, the mean and the standard deviation. This is a log normal, for example. But in principle, you can use a histogram, and you can refine even the height of each beam in the histogram. But let's start simple. This is just a log normal distribution. So what happens to the Fourier transform? You will see a formula that looks complex, but in the end, it is not. It is still a function of the distance within the crystal up to the maximum distance, and HKL, now it's a function of mu and sigma, which log normal mean and log normal standard deviation. So we have these two parameters to consider, and this is the expression. Now you say, oh, ugly, terrible. I cannot do that. It looks complex, but it is still a third degree polynomial, because the sum here runs from 0 to 3, and the third power of the distance is here. So in the end, we only changed the coefficients. And it's not so complicated. If you say, what is the shape, for example, sphere again, you can calculate geometrically the coefficients, h0, h1, h2, h3, and these are fixed as far as you believe they are spheres. You don't like spheres, you want to make cubes, coefficients for cubes. Octahedra, write the coefficient for octahedra. Any shape virtually, okay? In the end, it's a function of two parameters only, mu and sigma. So with Topaz now, we don't refine anymore the integral breadth parameter L vol, you remember this quantity, it's a bit ill-defined. We refine two coefficients, mu and sigma. So we don't play anymore with the Lorentzian width, Gaussian width. We believe it's spheres, and we refine mean and standard deviation. I like this approach. This is a physicist approach, that you must rely on a model. You have to put your face. You say, okay, I believe this is true. And then you test this, or you falsify this, of course, right? But you don't just use vague, ill-defined parameters. So let me show you how it works. With the Topaz, you include this macro file, which is available among the files you can download. And as it is easy with Topaz, when you write a macro, whatever macro, you can include it with a .inc file. It means Topaz carries along all what is in this file. And then you call the macro with the name you gave it. And as you see, this macro has just two parameters that Topaz will optimize. And if you're not satisfied with mu and sigma, because I don't know how much you know about log normal distribution, but the log normal mean is not the mean. It's the log normal mean. So there are simple formulas that from log normal mean, log normal standard deviation, they give you the regular mean and the regular standard deviation. And these are the simple formulas. Again, you can use Topaz to say, please calculate this for me. And this is the simple expressions you can use. Okay, let's see this in action on this sample. You have already seen my beloved PDF3 items in the ICTD database that you download the data and the information as well. And this is the result. Now, the fit is pretty good already. It cannot be better because the data are a bit crappy. Can I say that? I already said crappy. Okay. So I'm not judging the quality of the data, but definitely below par. But that's it. And you see now, the double void gave 9.5, which is way higher than it should be, whereas now we are more comfortable with about 6, which is not too far from 7. That's enough for the quality of this data. I will show you better quality data, which you can obtain your home instrument, synchrotron, and in the files you can download. Okay, now let's move on with strain. Now strain adds some complexity, because about strain we know some general features about how inhomogeneous strain act on the broadening of the peak. So keep in mind this. If the strain is homogeneous everywhere, you're sort of, squeezing or pulling your crystal and you will just shift the Bragg peaks, okay? Now, when it is inhomogeneous, so it changes from point to point and even different along different direction because of dislocation, rim boundary, whatever it happens in your crystal, then you have some broadening of the peaks. And then you have a Fourier transform component. Now, the expression, which is pretty general, is this one. Sorry, it is very small for those who are sitting in the rear, but it is just an exponential function. And in the exponential, there is the square of the reciprocal space vector, which is basically the position of the peak, right? And this quantity, which is the mean relative square displacement, we should say relative, because it's the displacement between any 2 points. But now we don't treat this displacement as a constant, because the strain is inhomogeneous. So depending on where you are, this displacement will be different as a function of L, the distance between the 2 points. So it's a complex thing. And in fact, instead of talking in terms of displacement, you can talk in terms of mean square strain. It's the same. So depending on which language you like to talk about, you can talk in terms of strain or displacement. Strain epsilon is delta L over L. So the variance is strictly related. So what makes this thing complicated? As I said, this is not a constant as we have treated with the double void, that E0 quantity. This is not constant. I show you an example. This is a crystal with a dislocation. I hope you can see it. It is sitting right here. This is the effect of the coalescence of 2 ceramic nanocrystals which trapped the dislocation in between. Now, if you measure the distance between any 2 points, a distance L, in different parts of the crystal, of course, that distance will be different, not a constant. So the displacement will be different and dependent on the distance, and also dependent on the direction. For example, if you look at the dislocation from top, from this direction here, you don't see the dislocation, right? Because the distortion is not there. Like in electron microscope, you turn a crystal in the right way, you look at the edge dislocation from top, and you don't see it because it's perpendicular, and then you don't see the defect. This means that you have an anisotropy in the strain, which is reflected in the peak broadening. And we can encode this anisotropy with a quantity that you can calculate called contrast factor. in the end, the contrast factor is functionally equal to the Stephens coefficient you have seen in the morning. But the result is different. And the coefficients need not to be all positive. And if you make an hypothesis of the type of defect, you can calculate it exactly. This is the big difference. Okay, so let's talk about theory and how TOPAZ can digest, swallow this thing, what is in the sausage, right? So this is the expression for the variance of the displacement field distribution. So is the width of this related to the width of this distribution. And remember, you have one such quantity for every distance L along every direction in the crystal. Quite many things. So it's related to the average dislocation density, that is a number that maybe you want to know. The cutoff radius, which is more or less the extent of the strain field of the dislocation. Burgers vector, which is known from the unit cell parameter, so it's not a variable. A function, which is a known function. Don't care about that. It's a function. It's been calculated. And this contrast factor I just mentioned before, that can be refined, adjusted empirically, like with the Stephens coefficients, or it can be calculated. So in the end, how many new parameters have we added in TOPAZ, like with this instruction here? Just 2. Typically, we add dislocation density and cutoff. You might add the third one, because you can even tell the difference between an edge dislocation and a screw dislocation. This comes to a comment I have proposed in the morning when I told you that the elastic strain anisotropy is not the whole story. So this method by Stephens and Poppa, considering the elastic anisotropy of crystals, is true, but there is also the geometrical anisotropy of the defect. And clearly enough, edge dislocation and screw dislocations are different. One is a pure shear field, screw dislocation, and the other is compression and tension. So, and is different orientation. So you can calculate the coefficients for edge and for screw, and even try to see how many edge and how many screws you have in your material. Okay? Okay, that's it. One more plot you can produce with this theory is this, that is I call Warren plot, because it has been proposed for the first time in 1952 by Bert Warren, and then forgot for many, many years. Why am I showing you this? I will give you examples and quote dislocation densities, okay? But my advice is do not believe in those numbers blindly, because you are sort of overestimating this density, because you assume that all the broadening is due to dislocations. You might have other sources like the grain boundaries or other things. So keep this dislocation density as a sort of upper bound to the real value. And you might even use this theory without dislocations at all, because in the end you have to fit the data. So if the model works, you can make a sort of effective use of, you can use dislocation to measure something else. So to avoid this problem of interpretation, you can produce this plot, which is not telling you the dislocation density directly. You will know you can do it, but it's telling you what is the variance or the standard deviation, as you see here, of the displacement distribution. And this quantity is interesting. I will show you. First of all, it shows the anisotropy. You see it's larger for 111 direction than for 200 direction, because this is an example, I don't remember which example, for a material which is stiffer along 200 and softer along 111. So you can tell the anisotropy. Then, in this plot, if you take the slope, this is the strain. And if you extrapolate the slope at 0 distance, this is what you call true strain, also in terms of mechanics. So you finally take the result outside the fraction community. You can talk to other people about your results. So, interesting, what is the equivalent of the E0 instruction in TOPAZ? It means basically it is the same along all directions, unless you use Stephens model, but basically it is using this, a straight line in this plot. Now, I don't want to go into details, but you clearly see that the trend is not a straight line. The straight line comes from this uniformity assumed in the Williamson method and in the double void method. So it is not that it's wrong completely, you see, not totally different, but the details are different, and the details, I think, are important. Okay, you want to be convinced about this approach? I'm going to show you an example, and then we also run some example together, or step by step at least. But let me show one little demonstration. Is a paper and a work I liked a lot. It's published 10 years ago, because this was really very in-depth work on this approach of using this kind of slot here. It's a system, a material where there are no dislocations at all, but there is microstrain because of the surface, typical of catalyst. If you take catalysts, the surface is a source of strain because the coordination of the surface, the capping agent, whatever it fell on your sample, because sometimes it's kind of random, it is influencing the surface, and then the surface will be, pulling or squeezing the crystal. There is no fixed rule of what happens. And so you will generate some kind of microstrain effect. So we've been lucky to work with people who know how to prepare very good cubic nanocrystals. I give you the reference, you can read the details. But it's nice because with this cubic nanocrystal, we could also use molecular dynamics. Since these are metal nanocrystal, it works reasonably well for thermal and elastic properties. So we could simulate this Warren plot and compare it with the results from XRD. So this is the slide. This is the only one because it would take me an hour to show you all the details. So you see the real crystals on the side, the model with the strain field in color. So red, it means high strain, which of course is where? Is in the edges and the corners. It's quite normal. Under coordination, of course, is causing this. And then on the right, you see the Warren plot from molecular dynamics. I guess is in blue is the line, and the dotted line instead is the result of Topaz WPPM approach. And you see that more or less it's reasonably the same. I was super happy when I saw this. Of course, you can imagine, at some point you have to start trusting in what you do, and this was one of those times. Okay, good, guys. So it is sound. You want to see the whole paper is a PhysRev paper of 2015. We want to have a look at that. It's not among the paper I provide you because, in my life, I published more papers than I could ever remember. And many of them I regret. So be careful with producing too much. I could tell you stories of things I'm still, worried about. Someone will find out, what the hell have you written here? Okay. Okay. So, but this one is a good one, the one I mentioned. So now let's go to have a look at 2-3 case studies that you can go over with the data, because from now on, I'm providing you the data of these examples, and this is one of them. It has been ball milled fluoride, so nanocrystals of the order of 10 nanometers, and dislocations definitely there, and some grain boundary effects as well. Let me say something about ceramic materials. Now I don't think it's a problem anymore, but when I was your kind of average age, so let's say 30 years ago, you talked with my colleagues in science and technology of material science and technology, and talking about dislocation in ceramics was kind of a joke, because only metallurgists say, no, we only have dislocations. And I always comment them, but why? Why is this not true? Then if you want to tell me that dislocation in ceramics hardly move, that's something, but it's not that they cannot be there. Actually, it turns out that the materials with the highest dislocation density possible are ceramics. If you want to play with this, cuprite, Cu2O. And the reason is because it has a very low shear modulus. So the material is very easy to shear, and so it's full of dislocation if you manage to introduce them. So if you crystallize it, probably don't find any. But if you ball mill it, for example, it makes a hell of a number of dislocation. And of course, they don't move easily because it's ceramic, but you can create them. So this is just to say these locations are everywhere, but remember, in your material, only rarely it will be the only source of broadening. So you better use that Warren plot if you want to have the total information, let's say. The dislocation density, keep it there with a grain of salt, is an upper bound. Okay, now, this is the result using the double void approach we have already seen before. And we were kind of disappointed because there is some discrepancy in some peaks which are too broad or too narrow. So there must be some anisotropy, not large, but it's there. But especially the size was kind of wrong. You know, we're counting 20 nanos and instead it should be like 10. So now I am using the approach I just described. And so with the convolution approach, and this is the result. I'll go over the details now, so don't worry, there's too many numbers here, but you can already see that the mean size, the diameter, is 11 compared to 10. So now the number is much closer to what another technique is telling us. And instead of having nonsense parameters on strain, you at least see values of dislocation density 10 to the minus 6, minus 2, 1 times 10 to the 16 per square meter. It's a reasonable number. Now, do you know how you count dislocations? Basi, any of you knows? There are two methods, which are not exactly the same. One is you measure the length of all dislocations in a unit volume. And of course, the units will be meters to the minus 2, right? Length divided volume. Another equivalent is you imagine a square meter surface and you count how many dislocations cross it. And then again, it will be number over square meter, meters to the minus 2. And for materials with a lot of dislocation, 10 to the 16 per square meter is a reasonable number, just to give you numbers. And this is the number. Here you can see there is a cutoff of about 3 nanometers, which also makes sense with this high density and particles which are not bigger than 11. And this Fe is the fraction of edge dislocations. These are mostly edge dislocation. It's a number from 0, screw dislocation, to 1, all edge dislocation, is 0.7. It's not that I believe too much into this, but it means that the model works reasonably well. Okay? Now, in a bit more detail, this is the size distribution. You see the mean, as I said, 11 is close to what we see in TM. And the double void was 21. And we know that partly because of the pseudo-void line profiles which don't work properly, but it's also because it's a different mean. Remember, it's a fourth moment to third moment of the distribution. You see in the formula here. And so even if you calculate it the right way, it will not be the arithmetic mean because it's a different mean. Fourth moment to third moment is different from first moment. And in fact, the number is different. And then, if you like, the Warren plot, I said, this tells us something about the anisotropy, even on a qualitative level. It means you see more displacement along 111 than along 200. In fact, if you take fluoride and many binary compounds, salts, oxides, this is a common feature that the direction, which is soft, is along the body diagonal of the cube, so 111 direction, whereas the stiff is perpendicular to the cube face, which is completely the other way around than cubic metals. Opposite behavior. And you can see it immediately. If you're wondering what happens when the system is not cubic, don't worry, there is calcite as an example, and so you can see also something not cubic. Okay, calcite. That's another example, and in this case also, the size was definitely overestimated, 22 respect to about 8 to 10, that we can clearly see in TM pictures, more or less, what is the size of the crystalline domains, you know. By the way, we call them coherently scattering domains. You know, this is a terrible term because with the word coherent, we mean many things, sometimes not the same things. So you talk to synchrotron physicists, and coherence for them it has to do with time, or maybe it has to do with energy. Whereas you talk with a crystallographer, and maybe coherent it means the phase in the crystal. So more, let's call it a geometrical feature. So this is my definition, by the way, because coherence, when you use powder diffraction, is not an issue. We have beams which diverge like this and converge like this. I mean, coherence is not what we are after. So our meaning of coherence means within the same crystalline domain, basically. So you want to call them crystal light is also good. You want to call them domains or give it another name. But that's it. So in this case, also we see some peaks are too sharp or too broad. Another clue of anisotropy due to what? The shape of the crystal? It might be. Or it might be strain. Again, we use spherical crystal very frequently. And this is an assumption that sometimes is sound, like with the cerium oxide powder I've shown you in the model. You can see in the TM, spherical, more or less. Many times this is just a sign of ignorance. If you think of it, if your material is made of so many shapes, the best you can do is to change technique, maybe go to something in another school, go do something else. Or if you really want to use powder diffraction, you try to use a sort of average model, but be always careful, because the average is not always a good thing. Here I should quote the Italian poet Trilussa. Some of you who are Italian will understand what is it, but there is a poem on this telling when the mean is a meaningful mean or not. Okay, I'm going on in this way, but you can imagine cases when the mean makes no sense. Make a bimodal distribution, and the mean is maybe in the middle. Okay, Trilussa was a bit more funny, but the concept is this. Okay, so using a mean shape, it depends. Sometimes it works, sometimes it doesn't. With milling, it works reasonably well because the shape of the fragments is what we used to say equiaxial. That means more or less approximate a sphere, but it's not a sphere. So this is the modeling now using the convolutional approach. And now you see the size value is making more sense. It's about 8 nanometers like what TM sees. And on top of this, we have also information on the strain. So let me show you first of all the distribution of sizes. And you see very well about 8 nanometers, and this is about what TM sees. Whereas the L-vol, the common volume, the volume average, it's larger, it's in the order of 13 or 14. What about the microstrain? This is interesting because it's not cubic, okay? And calcite is heavily anisotropic, optically anisotropic, elastically anisotropic. So this is the Warren plot and the anisotropy factor. This one is how this contrast factor changes with the 2 theta angle with Miller indices. And these are this Warren plot along the different directions. So if you look at the color, you see that the OOL direction is much softer than the 012 direction, for example. No? So you can have this kind of information. And if you look at the crystal structure of calcite, you clearly see that there is this layered structure somehow, explaining why this long axis C direction is much more soft than the others. Okay, and then finally the example I've shown you in the morning, the ball mill iron alloy. You remember that we were kind of disappointed twice because of the anisotropy of strain causing this very bad profile fitting. Some peaks are broader than the model and some other are narrower than the model, so clearly it doesn't work. And the size, which is here, is you see about 26, the L-vol, and the real one should be more around 9. So now by using this model, we get much better fit here, and you get the right size, about 9 nanometers as in TM, this location density, which still makes sense, and it is all reasonable. Let me show you the size distribution centered around 9, and this Warren plot. The nice feature of the Warren plot, if you have memory from the previous slide, now it is the 200 direction, which is soft, and 111, which is stiff, because this is the anisotropy of iron. It's opposite than the fluoride, just the nature of the elastic anisotropy. So for iron, stiff, main diagonal, soft, cube face. Fluoride was reverse, the opposite. So it is not a small feature, something you might miss. If you use this approach, you see this immediately, which is good. Tells you what kind of anisotropy is your material. I will tell you a little bit more about what use you can do of this model, which is something I have started using recently. And in this, there is one paper in particular I want you to look if you want to learn more, which is a paper called the reference material for blah, 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 blah. And it's based on data from ID22 and ID31 especially, and some lab instruments. So it's also a very nice comparison among different instruments. So, okay, what would be the double void result? It would be this straight line. So you see that the double void approach with this average E0, it is not totally wrong. So more or less, the amount of average microstrain is not too far, but it's in the details which is different. And those details give you the different line shape. So the peak profile cannot be the same. Okay, so just to summarize this part, and then we move on with the hands-on. These are the two cases compared, fluoride and iron. And you see the opposite anisotropy, stiff and soft. I say soft to be more clear. I should say compliant, which is the correct term. You know? But however, who cares? And you see that in this case, you have 200 is higher displacement. In this case, you have 111, which is higher displacement. Now, what use you could make of these results? Well, you see anisotropy, and I told you that the tangent to this graph is a strain. If you take the value at different positions, it will be related to the distance between atoms at that length. But if you extrapolate to zero distance, this is what we call true strain, which is something you can obtain from other technique and from modeling. So what we can look at is this. You see the tangent in zero. This can be called true strain, and it's interesting. You see the higher strain, for example, for iron in the 100 direction is expected, then in the 111, and the reverse for fluoride. Now, if you remember Hooke's law I mentioned in the morning, is this one. You know, the stress is proportional to strain through the elastic constant. Then, obviously enough, Young modulus and strain are inversely proportional. No? So the product is a constant, they are inversely proportional. So from the ratio between the strain, you can have the inverse ratio of elastic constants. Is this interesting? Yes, because from this anisotropy now, I will show you how you can estimate what is the yield stress of the material and what is the resilience. Now, I don't know how many of you are familiar with this term. So for those who are not, yield stress is the maximum stress beyond which a material becomes permanently deformed. So you might call it the elastic limit. The two things are slightly different, but we don't care. So you want to call it elastic limit? Call it elastic limit. So it's the maximum deformation you can store elastically in a material. This is important because from this number, you know how much elastic energy is in your material. And then you know the resilience. Resilience is the elastic energy stored in the material. So by just using as an estimate, don't expect this to be very precise, but by just using Hooke's law, you can calculate, show you for iron, you can do the same for fluoride, you can guess what the values of yield stress are. So you basically use the correct elastic constant, you can calculate, you Google iron and elastic constant and ask what is the value along 111, along 200. You ask it to ChatGPT, for example, will give you the right answer. Then you can see that there is a yield stress in the order of 2 point something gigapascal. Now, think of it. How can you measure the yield stress in a nanocrystal? It's not an easy task. Can you think of a nano machine pulling a nanocrystal? It's not easy. So it's nice that using diffraction, you can estimate something which is extremely hard to measure. And is it this real or not? In the case of metals, there are studies carried out over the past 20 years with different techniques and many times just wild hypotheses on what should be the yield stress in a nanocrystal. And think of it, it is much higher than in normal bulk large crystals, because when the size becomes very small, at some point you cannot break the crystal using these locations because it's too small. So the materials become kind of intrinsically stronger. There's much of the fuss about nanocrystal is also about because of this. So these studies like this one show that what is more or less the trend of the maximum stress depending on the size. And if you look at the value for 10 nanometers, which is here, you see that it's in the order of 2 to 3 gigapascal, which is more or less the value we find. But this is just a study that you see as a huge variability, whereas we measure it for this specific alloy. And then, if you believe in all of this, if you know the stress and you know the elastic modulus, very simple formula, square of the stress divided 2 times the Young modulus, you get the resilience, which is in the order of 13 megajoule per cubic meter, which is a huge resilience, by the way, huge. Okay, you want more detail, you want to refer to this paper, which is included in the folder, and is very recent, and is a material that has been fully characterized, so you can see the results for the material and also how all the techniques work. There is also a quite nice part of PDF analysis that Max especially collaborated, especially you watched it, that we didn't make strange things because you're the expert. Okay, so now let's see the application and so the hands-on. Then if we still have time and you're not totally destroyed, we can have a look, just quick look at 2 things I left out. One is diffuse scattering and the other one would be faulting, at least to tell you a few things about faulting. Not in depth, just how it is. So now, if you allow me, you see this, right? So I have to kill this, right? And then, okay, guys, look for the data. And let's start with this one, which is calcium fluoride, double void start. I think the meaning is quite clear, right? So we start by characterizing those fluoride data using the double void standard approach, okay? If any of you is trying to do it real time, it will not be difficult. And if you use JEdit in particular, it's easy. Because you take this file, which is exactly the file I provide you, I just comment what is in it. You see a very short file, not much more. And this is the instrumental part. You don't touch because it's been calibrated for our instrument. So forget about it. And this is the structural data for calcium fluoride. Basically, you have only 2 atoms. You're in unique positions. One is calcium and the other is fluorine. With the Bari-Waller coefficients, you see 0.47 and 0.67 taken from handbooks for bulk materials. So this is our starting point. And then the usual L-vol and E0 instruction for the double void model. The remaining phase is magnesium oxide, which is just a contaminant. Forget about that. But, you know, why not? There is a little bit of a sprinkle of MgO and we model it. Okay, so now how to work? You just do this and you load it in Topaz. Now, this is how you start. You just make first 0 step, and this is a starting condition. Okay, but let's imagine that you don't use JEdit and you want to do in a different way. You find this in the tutorial, but in this case, you stop, I stop, and you clean everything. So if I want to start from scratch, I open Topaz, run Topaz, and then you go to launch, no launch, but launch, and set input file. And then you look where the input file is, and you load it. And this is it. So it's easy. Use JEdit or other edits. You go straight from the editor to Topaz and back. Much easier. If you don't like or you don't have the editor, you just go to launch, set input file. It's identical. And now you run it, okay? So let me make it the way I prefer. So close this and go back to this and start again. As you see, very quick, doesn't take time to start. So now we run. It will be very fast. The IWP, which is a measure of the sum of squares, is huge, of course. It's 150. And in short times, it gets down to, you see, 7 point something. Okay, we want to keep this, but we might also have a look at the data in a different scale. For example, how they look like in logarithmic scale. You can see that there is this tiny thing which is magnesium oxide. Or we can look in linear scale. In linear scale, we will look more, not so nice, as I said before, because you see clearly that there is some problems here. Oops, sorry. That this is systematic error. Remember, when you judge the quality of information, it's a counting statistic, grain statistic, and then systematic error. So you have to be very, very careful in believing all the estimated standard deviations as far as your residual is not white noise, which is something that never happens in the real world. Okay, so now this is the best that the double void model could make, and let's see, this should be data you already have seen in the slide. So you see, LVOL is this number here. If you're far, you don't read it, it's 21. And then there is E0 from strain is 0.0017, reasonable strain. And if you use Stefan's instruction, we already know you will do something better, but still the size value will not be very, very good. Okay? Is it clear up to this point? You understand it? Okay. Just to be redundant, you go to the tutorial and you find exactly these steps. You can go over the same steps on your own, if you like. And you see how the things change from the starting to the refined value. And then now we are here. Now we want to use the WPPM approach. To avoid confusion, for this I use another file. So you don't mess up with the different models. So from the same folder, let me pick up another file with a very clear name. Is WPPM size and strain dislocation. It's it. So now in this file you have the same instrumental part, because it's the same sample, same instrument, and same data. Those up here, XDD is the file name. And here now we have the convolution model called WPPM. So you see there is the instruction for refining mu, the log normal mean, and sigma is the log normal standard deviation. And then you can calculate the mean diameter, so the arithmetic mean, the standard deviation, and some average, surface average, volume average. You can calculate things. Then here, calculation assuming dislocation. Here I have to explain you something. If you want to use these locations and have a realistic number for the density, you need to know this contrast factor. Who gives you the contrast factor? Well, at the moment, there is no software for doing that. I have a Mathematica script doing this, and that usually doesn't crash. But I mean, it is not something standard, but you find many papers where these have been calculated, and maybe your material is isomorphic, so you can at least have a reasonable starting point. If your material are cubic or hexagonal, you find tables for these coefficients, so you have the right thing. If it is lower symmetry, well, help yourself somehow in the literature. Maybe ChatGPT can work out for you this. So flow rate is cubic, so you can easily find them. And these are the number, you see these coefficients, A, B. These are the coefficient of the contrast factor. I don't explain more than this. The quantity that we have to refine is the cutoff, which is the effective cutoff of the dislocations, the dislocation density again, and the type, the character of dislocation, we used to say. If it is 0 is Q, if it is 1 is H. That's it. It's these three parameters, no more. We can even calculate this contrast factor, the invariant part. This formal name is called invariant, to see anisotropy, the difference. But forget this. And at the bottom, you can create the Warren plot. And once you have created this plot, you can plot it using any graphical editor you like. Okay, that's it. So let's try this file. But let me, keep in mind this number. With double void, it was 7.5. It's not going to change much because anisotropy is not very strong in this case. Okay, it went down to 7. So we gained from 7.5 to 7. That for Rietveld analysis, believe me, something. You don't throw it away. I mean, and yes, we do see that the fit, the fit is much better. Yes. Let me show you again square root. Yes, and now there is no too broad or too narrow peaks. So we picked up the right anisotropy somehow. So let's have a look at the results now. And let's start from the sides. And here you see a much more reasonable 11 nanometers up here, 11, whereas from TM we had something like 10 to 12, so it's exactly that number. The volume average is 16.6, so it's larger as it should. Double void was 23, 26, I don't remember exactly, because on top of using the volume average, it's using, pardon me, wrong line shape for the peaks. Dislocation density, 10 to the 6, 16 meters minus 2. So remembering this number is in units of 10 to the 18. So to have 10 to the 16 is the second digit after comma. And that's it. I mean, I don't want to comment more. In this moment, the software has also created the Warren plot, or just to show you how it works. It should be here. Yes, Warren plot. And so it's just a double column. You plot them and you have these curves for the different directions. So it's not very complicated, and you can use it with the examples.